is given, then how to find the charge enclosed by this surface, and when potential is given, and how to find the charge enclosed by the surface. So like that, some problems we solved in the previous classes. And so that is one way of one type of application or one type of problems based on that. Next, with the help of this Gauss law, actually we can calculate this. We can calculate the electric field due to certain regular objects. Like already we derived the electric field due to infinite line of charge, and we defined due to the sphere, and due to the infinite plane we derived already in the electric field discussion, right? And so those expressions we can again derive by using this Gauss law more easily. So that means the general procedure for deriving, that means I will explain some of those derivations. So with the help of those derivations, we can solve some lengthy problems also. Like generally we derive for this uniform distribution of the charge. Then even if you are taking the non-uniform distribution, then you can solve those problems there based on that, right? And so now just in that, just we need to consider a Gaussian surface. We know this Gauss law can be written as phi is equal to the surface integral of like E bar dot ds bar, and which is equal to 1 by epsilon naught times the charge enclosed, right? So that means in order to apply this Gauss law here, first we need to assume a Gaussian surface, and through that Gaussian surface we calculate the flux. So in general our Gaussian surface, or either we consider like a spherical Gaussian surface, or we consider like a cylindrical Gaussian surface in for a regular objects. Like if it is a point charge is given or a spherical charge distribution is given, then we consider the Gaussian surface in the form of a sphere. Or if a line of charge, or if a plane of charge is given, then we consider like cylindrical Gaussian surface. And so then if cylindrical spherical surface means then only one surface will be there, then we can calculate the flux passing through the such a surface. And if cylindrical Gaussian surface is considered, then we need to calculate the flux passing through this curved surface and flux passing through the plane surface separately. And from that we need to calculate the net flux here. And by calculating the net flux, we can calculate this electric field. Now that means we are going to derive an expression for this electric field now by calculating this flux here, and we are going to calculate an expression for this electric field. And so now let us see how to apply this Gauss law and how to derive that. So here first I am taking this application of Gauss law, Gauss theorem, the electric field due to the infinitely long straight charged wire we are taking here. So this is an infinitely long straight wire here. It is tends to infinity, and it is having some linear charge density, say lambda. And so now here, so we are taking such a cylindrical Gaussian surface here. This is a cylindrical Gaussian surface. Suppose if you want to find the electric field at a distance r from this wire, so we need to consider a Gaussian surface of radius r here. So this is a Gaussian surface of radius r. So this is an infinite wire, and we are taking a Gaussian surface. And if you want to find the Gaussian surface of radius r, then we need to find the Gaussian surface of this radius r here. Suppose say we are finding this electric field here. Suppose now then we need to find this distance. If you are taking this radius as r, that means if you want to find the electric field at a distance r here, then we need to take this cylinder of radius r, and we are taking suppose a length L, right? And so now this is our Gauss law here. We need to apply the Gauss law like this. And so now here first we should observe that here it is having these two types of surfaces. One curved surface, this curved surface, and then this plane surface. Here one plane surface is there, and here one plane surface is there. So this is our Gaussian, that means Gauss law here, which is nothing but this phi is equal to surface integral of E bar dot ds bar is equal to q by epsilon naught. Now we are calculating this flux here. So flux through the surface A plus flux through the surface B and plus flux through the surface C. So A, B are the plane surfaces, and C is a curved surface, right? And so now here it is the integral of, for the plane surface, let us consider here. For the plane surface, if I consider, now observe here, the electric field is away, perpendicular to the rod and away from the rod, line of charge, that we already know that. And so this will be the direction of electric field at the surface A here. And now the direction of the area vector at the A will be along this direction. So ds bar. So now we can observe that at this point these two are perpendicular. And so when these two are perpendicular, we know flux passing through the surface will be 0. So that is nothing but what we are writing. And similarly for the surface B, if I consider, the electric field will be away from this line of charge. Away from the line of charge means it will be like this. And now the ds bar will be along this direction. And so again for this plane surface B also the flux will be 0. That means I can conclude that the flux passing through the A and flux passing through the surface B will be 0. And next let us take the surface, that means curved surface C, let us consider here. Now the area, this E bar will be, electric field will be away from the wire, and ds bar is also, now it is perpendicular to the wire at any point here. So at any point you can conclude that ds bar and E bar for the curved surface will be perpendicular, that means they are along the same direction, both are perpendicular to the wire. And so that means angle between this ds bar and E bar at any point on the curved surface C will be 0. So that is nothing but what we are writing here. For surface A, E bar, that means E into ds into cos 90. And for the surface B also E into ds into cos 90, and for the C E into ds into cos 0. And so these two terms will be 0, and only this term will be there, and this term we are writing this side here. That means the E we are writing outside, then E into integral of this C you will get, ds you will get. Ds is nothing but curved surface area we need to write here. So you can write it as 2 pi RL. L we are taking this length of the wire, and R is the radius here. So now this is the flux calculation. That means we calculated the left hand side term in Gauss law here, E bar dot ds bar. So E bar dot ds bar will be equal to E into 2 pi R L. And next we need to calculate this Q value here. Right hand side calculation we need to do here. So now this Q by epsilon naught we can write as, Q is nothing but we can write it as lambda L, because we are taking this Gaussian surface of length L here. Then charge enclosed by this Gaussian surface is nothing but lambda into L we can write, where lambda is a linear charge density we can write there. And so that is our Q by epsilon naught value. Then by using Gauss law we can equate them. So E into 2 pi R L is equal to lambda L by epsilon naught. And from this we can write this E is equal to 1 by or lambda by 2 pi epsilon naught L. And this is nothing but generally we express it as 2k by lambda. That k is nothing but 1 by 4 pi epsilon naught. In vector form we can write like this. Right? That means it is away from this, it is in the direction of this R bar. R bar is nothing but unit vector, unit position vector. This is a unit vector here, position vector, position of that point. So here we are writing this direction. The direction of electric field intensity is radially outward from the positive line of charge. For negative line of charge, it will be radially towards this wire. So that means here electric field, the electric field intensity is independent of the size of the Gaussian surface constructed. It depends only on the distance of the consideration. That is, the Gaussian surface should contains the point of consideration, right? This we already discussed in the Gauss law when we were discussing the Gauss law itself. This flux passing through this Gaussian surface does not depend on the size of the Gaussian surface. It depends on this it depends on this charge enclosed there. Majorly depends on the charge enclosed by this Gaussian surface. So this is the intensity of electric field due to the line of charge, lambda by 2 pi epsilon naught, or infinitely long. And or we can express it as 2k by lambda, where k is 1 by 4 pi epsilon naught we can write. This we already derived that by using our finite wire we derived previously, and from the finite wire we derived infinite and semi-infinite wires also, right? So this is a calculation by using this Gauss law. And next similarly let us take this plane of charge here. So I'm taking now plane of charge. So this is an infinite plane of charge having this surface charge density sigma. So now let us see this electric field intensity due to infinitely long thin plane of charge here. And so that means it's a thin plane and it's infinitely long plane here. So same again we are taking this Gaussian surface in the form of a cylinder here. Cylinder passing through this Gaussian infinitely plane. That means if plane is like this, for example, now our Gaussian surface, the cylinder surface will be like this. So which is shown in this diagram here. So cylinder is cutting this infinite plane here. And so now suppose if you want to find say intensity of electric field at a distance of say R here, or let us say here we are taking total length as The total length we are taking it as L, so then you can consider this Gaussian surface like this. The radius of the Gaussian surface, suppose say R, and this is the radius of the Gaussian surface, and length we are taking it as L, right? And now here let us again here three types of surface are there. A, which is a plane surface here, and this is B, another plane surface, and this is the curved surface C here. So that means again two types of surfaces, two plane surfaces and one curved surface is there, similar to that of our previous calculation, right? Now let us see the flux calculation here. For example, if I consider the plane surface A, what is the direction of intensity of electric field? I think here you can consider that clearly for the surface B. A and B are same only, so I will explain at the surface B here, right? And so now here you can observe that the intensity of electric field due to this plane of charge will be away from this plane, right? Since it is a positively charged plane. And so now it is away from the plane like this. So E is perpendicular to this plane and away from the plane. So direction of E bar will be like this. And then this ds bar is also along this same direction here. So E bar and ds bar are in the same direction for this plane surface B, and the same thing for this plane surface A also. E and ds bar will be in same direction. And whereas if you consider the curved surface C, the E bar will be along this direction and ds bar will be perpendicular to that. And so now in this case, the flux passing through this curved surface will be 0 here. Only flux will be there passing through the plane surface. Whereas in the previous case, the flux passing through the curved surface will be non-zero. Flux passing through the plane surfaces will be 0. So that depends on the given case, whether the flux passing through the plane surface is 0 or curved surface is 0, right? And so here again I am writing this total flux E bar dot ds bar as E bar dot ds bar for the plane surface A and for the plane surface B, and plus for the curved surface C. And for the plane surface A and B, this E bar dot ds bar you can write as E into ds into cos 0, E into ds into cos 0 for B also. And for curved surface C, then this will be 90. And so then this is nothing but E into ds into integral of ds. That means we are adding these two terms here, A and B. So 2E into integral of ds you will get. The ds is nothing but you can write it as pi r square. So then E into 2 pi r square we can write. So this is the total calculation of this E bar dot ds bar value. That means on the LHS side. Now let us see the calculation for this Q value, RHS side. So that Q value we can write as sigma into pi r square. That means now whatever the here this Gaussian surface, the charge enclosed will be is nothing but charge enclosed within an area of pi r square. And so that pi r square, in the sense we can write it as sigma into pi r square. So that means that Q value we can write as sigma into pi r square by epsilon naught. So let us equate the RHS and LHS side here. And so then you can write this 2E into pi r square is equal to sigma into pi r square by epsilon naught. And from this E value is equal to sigma by 2 epsilon naught we can write. So this also we know already. Just we are deriving by using this Gauss law here. E is equal to sigma by 2 epsilon naught. In vector form you can write this as some L bar or R bar, R cap you can consider here, perpendicular to, which is a unit vector perpendicular to that, perpendicular to plane. So the direction of electric field intensity is normal to the plane and is away from the positive charge distribution. For the negative charge distribution, it will be towards that plane. So then this note is nothing but again for the Gaussian surface here, independent of the size of the Gaussian surface. So that is in case of this like say infinite plane of charge, right? So for the infinite plane of charge, the intensity of electric field will be sigma by 2 epsilon naught. And regarding this, we need to remember that we already know that this expression is independent of distance of the point from this plane here. Whether you are taking a point here or whether you are taking a point here, it doesn't depend, provided the distance of that point must be very small when compared to the size of this size of this plane here. Like suppose say this plane is of size say some 20 meters, and we are taking a distance at 15 meters or 25 meters for example, then you can't take this as infinite plane when compared to the distance, right? If suppose this side of this plane is 20 meters and you are taking at a distance of say 10 centimeters or 5 centimeters, then you can consider that as infinite plane. So that depends on this consideration here. So infinite plane in the sense the distance of the point where we are considering the calculating the electric field, the distance of that point should be very small when compared to the size of the plane or the dimensions of the plane there. Then you can take that as infinite plane. And so next let us see this. Here actually what we are taking is infinite plane of charge. Infinite plane of charge means that charge will be there on the only one side of this plane here. Suppose if I am taking this as a plane here, this charge will be there only on this one side here. So the charge is there only on this one side of this plane here. So then we consider it as a thin plane of charge here, and it is sometimes it will be mentioned as non-conducting. So that if the Gaussian surface is like this here, if it is cutting an area like this, and so that we are writing only the sigma into pi r square here, right? This is the charge we are writing. If for example charge is present on this side also, then sigma into pi r square into 2 we need to write, because this sigma into pi r square this side will be there and sigma into pi r square this side will be there. But here in this example, in this thin plane of charge means charge will be there only on this one side of this plane here. So that is a thin plane or the plane of charge means that you should remember here. And so that is sigma into pi r square we need to write here. Now if the charge is lying on the both sides of the plane, so let us see how to solve this one. So that is nothing but we can consider it as electric field due to a charged isolated conducting plane. And so that means whenever it is given as a conducting plane, so suppose if it is given as a conducting plane here, for the conducting plane if you are giving some charge here, so if you are giving some charge here, then automatically the charge will be distributed on the both sides of this plane here. Whenever you are giving some charge q, and later we derive an expression also, or we prove mathematically also. And actually, whenever you are giving some charge here, the charge will be equally distributed on this. And so sigma means then this side sigma surface density will be there, and this side also sigma will be there. Whenever you are giving, even if you are supplying only charge this side here, automatically that charge will redistributes on the other side also. That means both sides the charge will distribute. That is the importance of the conducting plane. So whenever they are giving it as a conducting plane of charge, you should consider that charge will be distributed on the both sides. And so here simply you can derive it as, now the Gaussian surface, you can take the same calculation as that of the previous. And so simply in that charge calculation, that means this flux we are writing as in the previous calculation, if I consider E into 2 into E into pi r square. This is a simple calculation I am writing here. Then this Q by epsilon naught. Now the Q we need to write it as E into sigma into pi r square into 2. Because if this is the Gaussian surface, if you are taking here, this side the charge will be there and this side also the charge will be there. Sigma into pi r square, right? By epsilon naught we need to write here. And so from this you will get this electric field as sigma by epsilon naught you will get. So that's the difference between conducting plane of charge and just an infinite plane of charge here. If they are giving just infinite plane of charge, then just we need to write it as sigma by 2 epsilon naught. If it is given it as a conducting plane, then you need to write like sigma by epsilon naught we need to write. That means you can carry out the same calculation for this conducting plane. The only difference is here. So here instead of this sigma into pi r square, we need to write sigma into pi r square into 2, because charge will be distributed on the both sides of this infinite plane, right? And that calculation only actually we can also explain like this. This is a simple calculation as we already derived for the infinite plane. You can proceed like this. You can simply write like this. This is another way of explaining that. Because why the charge will distribute uniformly on the both sides, even though here I said, even though you are supplying the charge to the one side of the plate, automatically the charge will comes to the other side also. The charge will distribute to the other side of the, if it is a conducting plane, remember that if it is a conducting plane, if it is just a metal plate if you are taking, and if you are supplying the charge to the one side, the charge will be distributed automatically on the other side also. So charge will be distributed finally on the both sides of this plane here. So the reason here is simply we say one of the important property of this conductors as the electric field, electrostatic field inside the conductor will be zero. So no field will be there inside the conductor, right? So here that is nothing but what we are explaining here. Suppose here I am taking a point Q here. So if I consider a point Q here, then for the point Q, now you can treat this as a two planes here. This side one infinite plane is there and this side one infinite plane is there here, right? And so now the electric field, resultant electric field at the point O, if I write here, the electric field due to this plane of charge will be like towards left you will get the electric field direction at this point O. So that means E1 will be say along this direction here. So this at point O I am writing here, like due to this first plane E1 will be along this direction, and due to the second plane this E2 will be along this direction. And so now this E1 plus E2, that means both are in opposite direction, so E1 minus E2 value should be equal to 0, because the electric field at the inside this conducting plate, our point O is lying inside the conducting plate here. This is the conducting plane we are taking, or conducting plate we are taking here. So our point O is the inside. So just what we are concluding is inside this inside the conductor, electric field must be 0. And so then E1 minus E2 value should be equal to 0 here. Or from this we can write that E1 plus E2 is equal, E1 and E2 are equal. Right, that we can conclude here. Now suppose if I consider a point Q on the left side of the plate, or point P on the right side of the plate, if you are considering, for example at point P I am considering here. Now the resultant field at this point is nothing but a resultant field due to this plane 1, resultant that means field due to this plane 2. That means now this we are taking as two planes here, two plane of charges, which we discussed previously for plane of charge means. So plane of charge means now we can observe that charge will be there only on the one side. And so now here this is one plane of charge and this is one plane of charge we can treat. So at point P, the electric field due to this first plane of charge will be away from the plane. It is, since it is a positive charge, and due to the second plane also it is away from the plane since it is a positive charge, right? And so now they both are in same direction, so we can add them. So E1 plus E2 we can write. So E1 is nothing but sigma by 2 epsilon naught plus E2 is nothing but sigma by 2 epsilon naught, which is nothing but sigma by epsilon naught we can write here. So that is the electric field on the outside this conducting plate here. And similarly for the point Q also. So the same thing you can write. Electric field E1 will be towards left and E2 is also towards left. And so net electric field is E1 plus E2, which is sigma by epsilon naught. So that is the electric field outside this conducting plate here. So that you should remember here. If it is a conducting plane or conducting, if charge is given to the conducting plate, then automatically charge will be distributed on the both sides, and so that the electric field inside the conductor will be 0. So the charge distribution will takes place like that, such that electric field inside the conductor will be 0. And so in case of such a conducting plane, the intensity of electric field you can write as sigma by 2 epsilon naught here, right? So remember the difference. Infinite plane of charge means sigma by 2 epsilon naught. Conducting plane of charge means, conducting plate means, then we need to consider it as sigma by epsilon naught. Conducting plate means. So conducting plate means charge will be distributed on the both sides of that conducting plane, right? And so now here let us take some combination of this infinitely plane sheets here. So that means now electric field intensity due to the two parallel infinitely long thin plane of charges. So we are taking them as a thin plane of charges here. And so now two thin plane of charges are placed parallel to each other. They are placed parallel to each other. Suppose say one is having the charge density sigma 1, other is having the charge density sigma 2. And we are assuming the case 1 like sigma 1 is greater than the sigma 2 we are taking here. So now here three regions we are defining. The region 1 on the left side of the two plates, and region 2 in between the two plates, and the region 3 outside this that means on the right side of these two planes here. And so now we need to write this electric field resultant electric field in those three regions we need to write. Suppose now let us consider the region 1. In region 1, if I consider, the electric field due to this plane will be towards left because it is positively charged, and electric field due to the second plane is also towards left because it is also positively charged. So E1 and E2 are in same direction. So the resultant electric field will also be in the same direction. So electric field we need to add here. E is equal to E1 plus E2 we need to write. This electric field in this first region here. And that E value we can write as sigma 1 by epsilon naught plus sigma 2 by epsilon naught. So which is nothing but sigma 1 plus sigma 2 by 2 epsilon naught. Sorry, this is E1 is sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught. And so then this is the resultant electric field here, sigma 1 plus sigma 2 by 2 epsilon naught we need to write. And at the region 2 if I consider here, so region 2 means now we can consider the electric field due to this plane of charge is away from the plane here, so it will be along this direction, and due to this second plane will be away from this plane here, so that is towards left here. So these two are in opposite direction, E1 and E2 are in opposite direction. And as we are taking the case like E1 is greater than, sorry, sigma 1 is greater than sigma 2, so then E1 will be greater than this E2 in magnitude. and so that the resultant field will be along this direction you will get. And so the resultant field we can write as E1 minus E2 we can write, or which is nothing but sigma 1 minus sigma 2 by 2 epsilon naught we can write. And next we are taking the region 3. The electric field due to this plane will be away from the plane, so this E1 will be towards right, and electric field due to this plane is also away from the plane, so that is also towards right. So now both are towards right only, and so resultant is also now towards right. And so therefore you can write this electric field as E1 plus E2, or sigma 1 plus sigma 2 by 2 we can write, 2 epsilon naught we can write here. So that is in this case when sigma 1 is greater than this sigma 2. And now let us take the case like when both are oppositely charged. When both the planes are oppositely charged, that means again we are placing the two infinitely planes parallel to each other, but they are oppositely charged. One is having the positive charge density and other is having the negative charge density. Now the same thing similar to that, just you need to identify the directions. Just you need to identify the direction of electric field due to the each plane, and the resultant field we need to write here. Suppose in the region 1 if I consider, electric field due to this first plane will be away from the plane, and electric field due to this negatively charged plane will be towards the plane. So E2 will be towards right. Now these two are in opposite directions here. Here again we are taking that magnitude of this sigma 1 is greater than that of magnitude of sigma 2, and so that we can say, we can conclude that E1 is larger here. So then I can write E1 minus E2 because both are opposite in direction. So then sigma 1 minus sigma 2 by 2 epsilon naught I can write. And similarly if I consider in the region 2, if I consider here, so in the region 2 we can write it as in the region 2 again identify the direction here. The electric field due to this plane will be, due to this positively charged plane will be towards right away from the plane, and due to this negatively charged plane will be towards this plane here. Now both are in the same direction here. So when both are in same direction we need to add them. Resultant field will also be in the same direction. Then E1 plus E2 we need to write, sigma 1 plus sigma 2 by 2 epsilon naught we need to write here. Similarly in the region 3, this side if I consider, electric field due to this positively charged plane is away from the plane, so towards right, and electric field due to this negatively charged plane is towards left. So then it is opposite direction, both are opposite, so electric field is E1 minus E2 we need to write here. So this is the electric field in these different regions when they are having this oppositely charged density here. Now let us take the case like both are having the same charge densities. Both are oppositely charged and both are having the same charge density. That means plus sigma and minus sigma. Just we consider the previously sigma 1 and sigma 2. Just if they are sigma 1 and sigma 2 are equal. Now in this case both are equal and opposite. So electric field in this region will be 0. No electric field will be present in this region. And similarly in this region also they are opposite each other. So no electric field will be there. And net electric field will be 0 in this region also. So only in this region that net electric field will be there. So which is nothing but sigma by epsilon naught. Sigma 1 plus sigma 2 is nothing but 2 sigma you will get. So then 2 will be cancelled. Sigma by epsilon naught you will get. So only electric field will be there in this region. So this arrangement you will get in capacitors. Remember that. In capacitors means, I think you have an idea. Capacitors means it consists of two plates. One carries a positive basic parallel plate capacitor. One carries a positive charge and other carries the negative charge. So you will get such an arrangement. So this case is now similar to that of a parallel plate capacitor, I can say. So that you will get this electric field only in between the plates. Outside the plates the electric field will be 0. Right? So that is the case when you are taking this combination of these planes here. So that means if they are oppositely charged here and they are having the same charge density, electric field in between the plates is non-zero. Outside it is 0. But if you are taking the case like this, both are positively charged, and in this case if I consider this E1 sigma 1 is equal to sigma 2, then electric field you will get the opposite case. Electric field in between the planes will be 0. Both are positively like charges and having the same magnitude of charge densities. And now the electric field in between the planes will be 0. So then there is no electric field in between the planes. And outside the planes, same electric field like sigma by epsilon naught will be there in opposite direction. So this side it will be towards left, and this side it will be towards right will be there, right? So that will be the case if they are having the same charge densities here. So that is when you are taking a combination of plane of charges here, right? So now let us take this electric field near the uniformly volume charged plane. That means now this what we are taking, all these cases are like thin planes. So that is why we are mentioning here itself a thin plane of charge here. And so even if you are taking this this is also a conducting plane here. So conducting plate means then it is generally thin only. For conducting plane, even if it is thin or thick, there is no difference here. This plane itself indicates that this thickness will be small. And so now we are taking that non-uniform, that means it is a uniformly charged plate here, that means plane of charge having some thickness d, considerable thickness d, and some charge is present throughout this volume. That means it is a non-conducting plane here, non-conducting plane of charge having some thickness and volume charge distribution. So previously we discussed only surface charge density there, only surface charge density will be there. That means charge will be distributed only on the surface of this plane here. Now in this, the charge will be distributed throughout the volume. So throughout this volume, the charge density will be there. So now here for this, we need to calculate electric field inside and outside. So inside and outside this planes we need to consider here. So that means here also we are taking the Gaussian surface here. Now first we are taking the case like inside. That means consider this. This is the infinite plane having this charge density rho, volume charge density rho, and thickness of that infinite plane is d. D is the infinite plane thickness here. So that is a consideration or information about this infinite plane, right? Now we are going to calculate electric field at a point inside the plane. So for this, say inside the plane means at a distance of r from the symmetrical axis. So this is this dotted line is a symmetrical axis here. So at a distance of r from the symmetrical axis, we are taking this Gaussian surface here. Now here, so we are taking the Gaussian surface of this length 2r. Now this is again our Gaussian surface is in the form of a cylinder. So cylinder, like similar to our this plane of charge calculations here, like this only, but the cylinder lies inside the plane only, because that is a thick plane we are taking here, and we are going to calculate this inside. So we are taking such a cylinder and it is inside, right? Now the electric field, the flux calculation, that again we are taking this Gaussian surface of area. This area we are assuming it as s, and this length we are taking as 2r, right? Got the idea about the Gaussian surface? Same cylindrical surface, same as that of our infinite plane calculation. This dimensions are, we are taking that length of the cylinder as 2r, and this cross section area, plane's cross section area, we are assuming it as s. Then this is our Gauss law. Now let us see the calculation of this left hand side here. So now this is integral of E bar dot ds bar is equal to integral of E bar dot ds bar for the left. That means this plane, and for this right and this plane, and for the curved surface. And for the curved surface, actually if you consider here, the electric field will be away from this plane here. The electric field direction will be like this, but the area vector will be, you will get like this, the area vector. So that the electric field, that means this is our ds value here for this, and electric field will be along this direction here due to the plane of charge. And so for this curved surface here, the flux passing through the curved surface is 0. So that is nothing but what I here 0 is mentioned here, right? Now similarly the charge enclosed here I am writing here. The charge enclosed is nothing but this volume into volume of this Gaussian surface into this volume charge density we need to write. And so volume of this cylinder we can write as this plane cross section area, we are taking it as s, and the length of the cylinder is 2r. So s into 2r into rho. So this is a charge enclosed here. And so let us substitute here, and as these two planes are identical, we can write this as E bar dot ds bar value we can write as, like similar to our previous calculations, this term I can write it as integral of E into ds into cos 0 we can write here for both of them. And so which you can write as integral of E into ds we can write. And such a two terms will be there. So into 2s into 2 we need to write here. So that is nothing but what we are writing. So this finally you can write it as integral of E into s we can write here. And such a two terms are there, left side plane and right side plane will be there. So into 2. So this is the total flux what we are writing here. So 2 into E into s is equal to q. This is our q term here. This q is nothing but s into 2r into rho by epsilon naught. Then this 2s will be cancelled. Then E is equal to rho into r by epsilon naught you will get. So this is field inside the uniformly charged plane here. So it depends on the distance from the symmetrical axis of this plane here, or axis of this infinite plane here. So that means it is a function of this r, or E is directly proportional to the r we can say here. So that means it is when you are traveling from the center to the symmetrical axis to the away from the axis, then electric field goes on increasing here. So that is this equation indication here. So this is an inside expression, inside a thick plane of charge having the volume charge distribution, right? So rho is a volume charge distribution. Now let us see the outside. So this is the inside formula. So now let us see the outside calculation. So outside calculation means a similar calculation, just this Gaussian surface will extend outside here. So now outside at a distance of r we are taking. Let's suppose this r is greater than this d, let us consider here, or d by 2. And so now we are taking this Gaussian surface of length 2r such that r is greater than this d value. And now it is outside you will get here. So suppose this point, this distance is r we are taking here. So same calculation will be there. The flux to the curved surface will be 0. Only flux to the plane surfaces will be there. And so I am writing here directly it as this left hand side calculation as 2 into E into S. Only difference will be there in this Q value, charge enclosed. So even though this Gaussian surface is there this much, but the charge is enclosed only within this volume here. So charge is enclosed here only. From here to only within this plane volume we need to consider here, right? Only this volume we need to consider there. So only this volume we need to consider here. So that this volume is nothing but we can write it as so that volume we can write as S into S is this cross section area into D, length of the cylinder here. This again cylindrical. That means it is enclosing inside this plane, inside this Gaussian surface. This is again you will get a cylindrical shape because our Gaussian surface is in the form of a cylinder. So S into D into rho. S into D will gives us area of cross section into length of the cylinder because charge is enclosed only up to this distance D here. So only that distance we need to write here. So S into D into rho by epsilon naught. And then this S you can cancel on both sides. Then E is equal to rho by epsilon naught into D by 2. And so that means outside, now we can observe that it is independent of D here. Inside, in case of a thin plane of charge, volume charge distribution, inside it depends on the D, it depends on the distance, but outside it doesn't depend on the distance here. It is a constant value, uniform field you will get here. So that variation you can represent like this. The variation of the electric field you can represent like this. So inside it is directly proportional to R. So you'll get a straight line passing through the origin, and outside you will get a constant value independent of R you will get. So that is in case of thin, that means thick plane of charge. So I think you got the difference here, thin plane of charge and thick plane of charge. Our most of the problems will be there based on the thin plane only, thin plane of charge only. If the particularly if they are asking like volume charge distribution, then you need to remember that. So in one of the previous advanced direct question is there, write the expression for this electric field inside this thin this such a thick plane of charge. That means this expression directly they asked as one of the question there. So that means this is a way of deriving that in case of a thick plane, right? So that actually based on this, you need to get an idea how to derive an expression for electric field if any charge distribution is given here. So these expressions, most of these expressions we already derived, except this thick plane here. Again, we are deriving in the sense just by using this Gauss law. If this is actually we are taking it for the uniform charge distribution, right? Even if it is a non-uniform charge distribution also we can derive expressions for this electric fields here. So after the standard derivations I will explain those how to solve in case of non-uniform charge distributions. Now let us see this electric field due to uniformly charged cylinder here. So we are taking a consider a uniformly charged cylinder of volume charge density rho and radius r. That means this is a uniformly charged density. Again this charge is there within this total this cylinder here. Charge will be there throughout this volume. So right. So that is a volume charge density meaning here. So volume charge density rho and radius r. Now we need to calculate this intensity of electric field here. So first I am calculating outside. The intensity of electric field outside the surface I am taking here. So this calculation is for this for any point r less than or greater than r, Gaussian surface will be cylindrical as shown in figure for any point inside the cylinder. So inside the cylinder means then this Gaussian surface you can consider like this. This is our Gaussian surface here. So for this Gaussian surface now we can write this as that means this is our total cylinder here. We are taking the Gaussian surface this one. So this is our Gaussian surface here. This small cylinder we are taking as a Gaussian surface, right? So now this Gaussian surface of length of the cylinder we are taking as L and radius we are taking as R. That means where we want to calculate the intensity of electric field, that point lies on the Gaussian surface. Generally we assume the Gaussian surface like this. Now again observe this. Again two plane surfaces will be there and one curved surface will be there. Now let us consider the flux of the plane surface. This top surface or the bottom surface. So flux of the top surface, if I consider, electric field will be radially away from this center. So it will be electric field E bar will be along this direction and dA bar will be along this direction. So both are perpendicular to each other. So we can conclude that flux to the Gaussian surface will be 0. That means flux to the plane surface will be 0. Top plane will be 0 and similarly bottom will be 0. And there will be flux only due to this curved surface here. For curved surface at any point, E bar and DS bar will be along the same direction. Radial outwards you will get. And so now this derivation calculation will be there here. That means the inside I can write this as, so inside this is the calculation here. Actually we need to write this, the total flux is nothing but E bar dot ds bar value is nothing but we can write this as flux through the plane surface like E bar dot ds bar into 2 because two planes are there plus flux through the curved surface we need to write here E bar dot ds bar. This is through the curved surface. Now flux through the plane surface is 0 plus for this curved surface you can write as E into integral of ds because both are in the same direction. So I can write this as E into that curved surface area we need to write here. So curved surface area is nothing but 2 pi RL. So that is nothing but what I mentioned here directly, E into 2 pi RL. So this is equal to Q in by epsilon naught. Now the Q in is nothing but charge enclosed here we need to write here, charge enclosed within this. So rho into volume of the cylinder we can write. So the volume of the cylinder is nothing but rho into pi r square L we can write. So then this pi r and L you can cancel here. So then finally you will get this electric field inside. So this expression here, the electric field inside this cylindrical surface. And now whereas if you want to calculate this outside, so then this is electric field inside, so inside it is directly proportional to this R here. So electric field intensity is directly proportional to R inside this Gaussian surface. Sorry, inside this cylindrical surface. Now this is inside expression. Now suppose if you were to calculate this outside here, the same calculation, flux calculations will be same, this term will be same as it is. The flux outside will be 0, flux to the plane surfaces will be 0 and flux to the only curved surface will be there. So again you will get the same. That means just I am writing here outside calculation. Outside, which is nothing but I can write this as R is greater than R. For this case we are writing here. So the flux calculation will be, left hand side calculation will be same. E into 2 pi RL we need to write. This is equal to now Q by epsilon naught. Now this Q value now we need to write here. So this Q value is nothing but rho into pi into capital R square we need to write by epsilon naught. Why we are writing capital R square? Because this charge will be there only within this volume here. So only this volume we need to consider here. And so that volume is nothing but pi r square L we need to write here. So that is pi r square L. Therefore you can write this expression as E is equal to, so then you can cancel pi and L you can cancel here. So rho into R square by 2 epsilon naught R, right? So that means outside it is inversely proportional to R we can write here. That implies this electric field outside is inversely proportional to R. So this is the outside expression and that is the inside expressions there. So inside it is directly proportional and this is the outside expression here. So outside it is rho into R square by 2 epsilon naught into R we can write here. So that is electric field inside and outside due to a cylindrical charge distribution. And so if you write the graph here, then you will get the graph like this. So it goes on increasing here. until the surface, and from the surface it goes on decreasing there, right? So I think you got the calculation here. So all these calculations are similar all, and most of the cases we are getting a cylindrical Gaussian surface only, and so then calculation you can understand it easily, right? So for some, in some cases the flux to the curved surface will be zero, and in some cases flux to the plane surface will be zero. That depends on the given situation or the given charge distribution. So you need to identify that flux to the which surface will be zero and how to write the charge enclosure there. And so next let us see this charge due to this electric field due to this uniformly charged thin spherical shell. So this also we know already. Again, by using this Gauss law we need to calculate here. So then first we are calculating at a point outside here. So this is a spherical charge distribution here. That means a spherical shell having this charge E. And now we need to calculate a distance of r from the center here. So that we are taking this dotted line is our Gaussian surface here. So here I am taking a small elemental area here. So through that small elemental area, the electric field direction will be away from the center. That means radially outward. And we know this area vector is also radially outwards, right? And so angle between them will be 0. And so now let us see the Gauss law application. Phi is equal to this. Phi E means electric flux here actually, because in magnetic flux, in magnetism, magnetic flux will also be there, that we represent with the phi B, and here we are writing it as phi E. Whenever you are you are identifying that phi E letter, it indicates electric flux, because such a similar magnetic flux will also be there. And so now it is integral of E bar dot ds bar is equal to q by epsilon naught. This is our Gauss law statement, and now we are applying this. E into ds into angle between them will be 0. So E into ds into cos 0 is equal to q by epsilon naught we are writing. And E bar magnitude value of this E will be same at any point on the Gaussian surface, because every point will be at the same distance r from the center only. So I can write this E outside. So then E into ds is equal to integral of ds is equal to q by epsilon naught. Now integral of ds is nothing but curved surface area of this Gaussian surface here. So which you can write as 4 pi r square. So E into 4 pi r square is nothing but the charge enclosed is nothing but total charge present on this Gaussian spherical shell only, right? And so that you can write it as that means q by epsilon naught. Q only the charge enclosure here. And so that you can write it as E is equal to q by 4 pi epsilon naught r square, which we already know here. That means we can consider it as a point charge placed at this center here, which is nothing but our shell theorem. So previously we derived by using our shell theorem, right? In gravitation also we derived by using the shell theorem. So this by using the Gauss law. So then we can write easily by using the Gauss law here, right? So that means by taking it as a point charge, we will get the same expression. By using this Gauss law also we can derive like this. And suppose if you want to express the same expression in terms of this sigma, where sigma is the surface charge density of this sphere. So then that we can write it as the surface charge density here. This q value we can write as sigma into 4 pi r square, and that we can substitute here. Then on simplification you will get this E is equal to sigma r square by epsilon naught into small r square you will get. So that is electric field due to this spherical shell for a point outside. Now if you are taking on the surface, so on the surface means simply you can write this small r is equal to capital R. Again the same calculation you will get here. Every step will be same. Just only difference will be there here. The Gaussian surface we are taking almost coinciding with this spherical shell here. Just outside we consider here almost. That means it is small r value will be slightly greater than this capital R you can consider. Or generally we know this small r, finally we substitute that small r is equal to capital R here, because the difference is very small. And so directly we are taking the term here. So that means previously the only difference is lying here. So previously here we are writing this E into 4 pi r square. All these steps are same. E into 4 pi r square, small r square. Here we are writing it as a capital R square here. So E into 4 pi r square is equal to q by epsilon naught. So, and so then q by 4 pi epsilon naught into r square you will get. So in terms of sigma, then electric field will be sigma by epsilon naught we can write here. So remember this, there is an importance for this. So for the conducting plane, we got the expression like sigma by epsilon naught, right? For the conducting plane of charge or conducting plate. And for the solid sphere, for the spherical shell also we are getting the same expression, sigma by epsilon naught. And later in the while discussing the properties of conductors, we will discuss about this. So there is an importance for this sigma by epsilon naught. So just outside or on the surface, we can say this electric field will be sigma by epsilon naught. We can write here. And next, if you are taking a point inside, so then again Gauss law, that means Gaussian surface we are taking just inside here, right? Then E bar dot ds bar is equal to q by epsilon naught here. Then E into ds. Then this term will be same. E into 4 pi r dash. We are taking that radius. So r dash square q by epsilon naught. But here the thing is the charge enclosed by this Gaussian surface value will be Gaussian surface will be 0 because it is a spherical shell. So charge will be there only on this outside here, right? And so no charge is present within this Gaussian surface here. And so then this q value will be 0. Charge enclosed is 0. So that this electric field will be 0. So electric field will be 0 inside this conductor. So that is nothing but we call it as electrostatic shielding. And later in properties of conductor, we will discuss more about this shielding here. And so now if we draw the graph between E bar and R bar, so that means inside no graph will be there. That means no graph will starts from small r is equal to capital R only. Inside the field is 0. So graph will be, this will be maximum at this point and it goes on decreasing. And sometimes they will ask about whether it is continuous or discontinuous. So you need to remember electric field due to the spherical shell is discontinuous. That means just inside this conductor it is 0. Just on the surface if you consider it will be a maximum value. And so then it is a discontinuous graph will be there. And so that is in case of this spherical shell. Now similarly let us take this volume charge distribution here. The electric field intensity due to a uniformly charged conductor, uniformly charged solid sphere. So this is uniformly charged Ly, that is. So this is Ly. So uniformly charged conducting sphere. And actually this charge is also uniformly charged in the sense we need to represent inside. This total charge, whatever it is represented here, that Q charge, that will be there inside this sphere. That means it is a non-uniform solid sphere. Because for uniform solid sphere, that means this is non-conducting sphere. For conducting sphere, whatever the charge you are giving, that resides only on the outer surface. That means charge is not on the outer surface, it should be there inside only. Inside this, that is the meaning of this uniformly charged sphere. Got it? Now same derivation here. The total, all the calculations will be similar. And so then if you are taking a point outside the sphere, then same E bar dot ds bar we need to take here. Then E bar dot ds bar, again both are in the same direction. If you are taking a Gaussian surface like this, then E into ds we can write here. So E we are taking outside, exactly the same calculation. Then integral of E bar dot ds bar q by epsilon naught. So then E, that ds is nothing but again 4 pi r square, the total surface area of this Gaussian surface. Then q by epsilon naught, and from this E is equal to q by 4 pi epsilon naught into r square. And suppose if you want to express it in terms of charge density rho, and so then this q value we can write as rho into 4 pi 3 pi r cube. And so the term you can substitute here, then you will get this expression here, rho r cube by 3 epsilon naught into r square you will get, right? So this electric field outside, so outside it is inversely proportional to this r square here. And you can also say that for the external point, it behaves like a point charge placed at its center, which is nothing but our shell theorem. So based on the shell theorem, we mentioned these expressions already. Now we are taking a point on the surface, right? Again the everything will be same. So only again the difference will be there here. So then E into 4 pi r square is equal to q by epsilon naught. So then you can write it as q by 4 pi epsilon naught into r square. Capital R square we need to write here. Just instead of this small r, we need to write this capital R on the surface means. So then if you substitute this in terms of the rho, then you will get rho into r by 3 epsilon naught you will get. This expression in terms of this rho. And then next actually we need to derive an expression for inside here. So that inside you can calculate like this. So I will draw this diagram. Now let us say this at a point inside here. At the point B inside this uniformly charged, this is also uniformly charged only. That means the charge will be there only inside. The diagram was mistake there. The charge is not on the outside. The charge will be there on this inside. Uniformly charged sphere. So that means here again we are taking a sphere of Gaussian surface of radius r here. Then we are writing like E bar dot ds bar is equal to q by epsilon naught. Everything here will be same. E bar dot ds bar is equal to q dash by epsilon naught. Now this q dash value we need to write here. So then this q dash value is nothing but we can write it as charge per unit volume into volume of this Gaussian surface we need to write. So charge per unit volume is nothing but q by 4 by 3 pi r cube into 4 by 3 pi small r cube, volume of this Gaussian surface. That is equal to q into r cube by r cube you will get. So then E is equal to this, you will get the integral of ds bar is nothing but 4 pi epsilon naught r square you will get. Sorry, 4 pi r square you will get. And if you substitute this side, then E is equal to q dash by 4 pi r square you will get. 4 pi epsilon naught into r square. Now this q dash value we need to substitute by using this. So then you will get this expression here. Electric field is equal to q into r by 4 pi epsilon naught here. Here epsilon naught should be there. So 4 pi epsilon naught into r cube into r cube. So that means now here this electric field at any point inside will be, inside this uniformly charged sphere will be directly proportional to this r here. And we can also mention that electric field at the center if I write, and electric field at the center of the sphere will be 0. That means when r is equal to 0, then it will be 0. And the variation of this electric field we can represent like this. So in internal for the when r is less than r, then it goes on increasing here. So this is a straight line. E is directly proportional to this r, and it reaches the maximum value. Now it goes on decreasing here outside. Q by r square you will get. K q by r square form only you will get. So this is a variation of electric field due to this uniformly charged sphere here. So this is a uniformly charged sphere, and this electric field we say it is a continuous variation. So inside field will be there and outside also field will be there. It is varying continuously. Whereas due to the shell it is a discontinuous variation. That you should remember, because in sometimes I will mention that options also whether it is continuous or discontinuous variations. So these are some standard derivations based on the Gauss law here. So then that means all these derivations we are deriving only when the charge distribution is uniform. So in the next class we will discuss about some applications of the Gauss law. Applications in the sense how to derive the electric field when the charge distribution is non-uniform. So then such a type of problems we will discuss in our next class. So then practice these derivations. Just again for the every derivation I will say the same thing. Just listen the class and derive all these derivations by yourself. And these derivations will be very similar, and so you can derive the derivations by yourself. If you got one derivation thoroughly, then remaining you can do by yourself, and that procedure is required for you. That means you should learn the procedure how to derive that electric field by using this Gauss law. Because for the next class what I am saying, that the non-uniform charge distribution, same calculation will be there. Only the charge inside we need to calculate that. Additionally, that additional calculation will be there. Charge inside we can't calculate directly like this. A volume into charge or area into charge density. We can't calculate directly like that. We should use again integration. So such a type of problems we will discuss in our next class. So practice all these derivations. Thank you.